Welcome back, student. Now today we'll discuss on Miller indices. It's a very important topic in your crystal structure chapter. As you know that metallic crystal structure are basically the various types, like 4 types generally, like simple cubic, body center cubic, hexagonal closed back. So basically there are 4 metallic crystal structure are there, and their atomic packing factor and unit cell, their coordination number, and different types of the calculation of C by A ratio. So already we covered this topic. Okay, now today we'll discuss on Miller indices, in which you can study on. Basically this is a tool. Actually, this is a, you can say that it's a tool, or by which you can it's basically forms a notation system. It's basically notation system. First of all, it's a notation system in crystallography. Now its crystallography is something that where crystal structure is analyzation take place, or a study take place. Okay, this is a crystallography. Okay, regarding crystal, the structure is the study is called crystallography. Okay, so it's basically forms a notation system in crystallography for planes in crystal lattice. So crystal lattice, like suppose this is one crystal lattice. Okay, so this is one crystal lattice in which that atoms are arranged. Suppose this is the atom that can arrange a particular and takes a cubic shape. So this is a lattice. So in a lattice, the how atoms are arranged, okay, so they give a particular notation system of a plane. Okay, that's why it is used, and that's why it is called Miller indices. So in one word or in one sentence you can say that it's a Miller indices. First of all, it's a notation system. Okay, it forms Miller indices forms a notation system in crystallography for planes in crystal lattice. Okay, and where it is used, and why it is used, because of to specify the direction and planes. So these are the atoms that are arranged. Now these atoms are arranged in a particular direction and a plane. So it is basically Miller indices used for that particular atoms directs to identify direction and planes. Okay, now these direction and planes could be used actually in lattice or in crystal. Now Miller indices can be identified with this term like H, K and L. Okay, H comma K comma L. Particular, if you want to represent H comma K comma L, that is basically a, and within the first bracket that represent a particular point. Okay, similarly within the third bracket, if you represent H comma A comma L, so that represent a particular direction. And so these are the nomenclature that you can use to identify the particular atomic arrangement of a particular, is it in plane or direction, or a particular family of direction, or a particular family of plane. Okay, now when you discuss a particular example, all this will be clear. Okay, all the things will be clear. So your now the Miller indices for direction. Miller indices for direction is particular a topic in which a vector or passing a vector r, suppose a vector r passing from the origin to a lattice point, can be written as also r is equal to ra plus r2b plus r3c, where a, b, c are the basic vectors and Miller indices will be r1, r2, r3. Okay, so fraction in r1, r2, r3 are eliminated by multiplying all components by their common denominator. Okay, similarly for planes, now what are the procedure takes place to identify, to represent a Miller indices for a particular plane? Now first your task will be that first you have to find the intercept of x, y, z of the plane along their 3 reference axes. So basically 3D structure, atomic arrangement are basically occurs within the 3D structure. So the atomic arrangement will be in 3D structure. So the particular arrangement, for a particular arrangement, you have to first identify the intercept point in x, y, z direction. of a plane. Okay, now next next task will be your express the intercept in terms of axial units. So that is equal to x is equal to pa, similarly y is equal to qb, and z is equal to rc. Now find, the next step will be you have to find the ratio of their reciprocal. So that will be, if the number is p, the intercept point is suppose p q r, then the reciprocal will be 1 by p 1 by q is to 1 by r. Okay, now the next step will be this reciprocal just convert into, these reciprocals will convert into whole number by multiplying each one them with their LCM. Suppose it's a reciprocal is 1 by p 1 by q and 1 by r, so in the denominator, so pqr, the LCM of pqr, what is the number of pqr, suppose 2 3 and 3, so that will be LCM will be 6. Okay, if you multiply with that each with individual with 6, then if you then convert into the whole number, you can convert into whole number with reciprocal. Okay, and then enclose the numbers in small bracket, and this represents the index of the given plane. Okay, this represent the index or Miller indices of the given plane. Okay, so this is the theory part of the Miller indices. Now when you see the example, the Miller indices will be clear to you. Now it's a very easy things that suppose here in this example what is given, that if the atoms, if the xyz intercepts are is given as 2 comma 1 comma 3, now you have to calculate the Miller indices. So intercept point, suppose this is the intercept point, so this is the atomic arrangement of the is a cubic unit cell, you know that. Now intercept point is given, that is 2 comma 1 comma 3. You have to calculate the Miller indices. So first step will be intercept point for x is equal to 2, y is equal to 1, and z is equal to 3 here. Okay, now take the reciprocal. The next step will be take the reciprocal of the intercept point. So first is the take the reciprocal of the intercept point, that will be, so 1 by x, 1 by y, and 1 by z, that will be 1 by 2, 1 by 1, and 1 by 3. Now that is basically the in the denominator part, the 2 1 and 3. If you get the LCM, if you get LCM of 2 1 and 3, that will be LCM will be 6. Now if you multiply with 6 with these reciprocal numbers, that will be the smallest integer. So after all, you can get that 1 by 2 into 6, that means 3, 1 by 1 into 6, that means 6, and 1 by 3 to multiply with 6, that means 2, and it represent with the first bracket. So this is the Miller indices in which the atoms are intercept in x y z direction, that is in 2 1 3. The Miller indices will be 3 6 2, and that is will be in first bracket. Is very important, that is will be first bracket, because the first bracket are used to identify two Miller indices for a particular plane. Okay, so particular plane, so this is first bracket. Now one more thing, that so negative Miller indices, suppose if the Miller indices like 0 comma minus 2 3, if it is suppose that, so it will be looks like, or it will be written as 0 2 bar 3. That means negative Miller indices values are denoted by a bar on top. Suppose HKL is your Miller indices, right? Here 362 it is given. Now 362 is your H comma K comma L. Okay. Now suppose Miller indices given that -2, -3, 6. Suppose. So that will be written also as 2 bar, okay, 3 bar 6, or H bar K bar L. Because of negative Miller indices, values are denoted by a bar on top. So negative values, -2 is your negative, -3 also negative. So that's why 2 on your bar on top. Similarly, bar on the top of that particular Miller indices number. Okay. So similarly, H on the top. so on the top as a bar, and K is a bar. Okay, so again, one interesting more point, that planes without an intercept are taken as infinite plane, so that is infinitive. We can discuss later on this. Okay, so this is the important point. So negative Miller indices values are denoted by on the bar, by a bar on top. Okay, now suppose these are the representation of a crystal plane in a cubic unit cell. Okay, and these are the representatives of crystal planes in a cubic unit cell in, so these are the defined plane, you can see it. Okay, now let's take an example on Miller indices. How do you calculate on a particular plane? So these are the Miller indices for plane as well as direction. So what it is used to identify the dislocation in crystal. So it is identified to use the dislocation within the crystal, because dislocation motion actually occurs within the material. So when the materials are dislocated due to loading conditions within the atoms, and the optical properties, the optical arrangement, the optical properties will be identified with the help of Miller indices, because it is optical properties depend on the atomic arrangement also, and the atomic arrangement or atomic arrangement plane, it's basically identified with the Miller indices and the direction also. So and the different reactivity and surface tensions also I identify within the Miller indices. So okay, these are the uses part of the Miller indices. Now let us take an example. Actually Miller indices used, okay, as you know that Miller indices are used to specify direction and plane, right? So for the direction part, as you know, this is a cubic cell. So this is a cubic cell in which the atoms are arranged in a particular 8 corners of the cubic cell. So this is the atomic arrangement. So in this way, now it is basically to specify direction and plane. Now suppose a particular vector that is basically r here, now it is moving from the direction plane, that is 0, 1, 1/3, and that is 2/3, 0, 1. If it is happened so the distance, the vector will be calculated as 2/3 minus this one, 0 minus 1, and 1 minus 1/3. So after all, you can get a particular number that will be 2/3 minus 1, 2/3. Okay, you have to convert into the least, you have to convert into whole number to multiply in the LCM. Okay, so in the denominator part, so 3, so LCM will be 3. So 2/3 into 3 minus 1 into 3 and 2/3 into 3, the integer will be 2 minus 3, 2. So Miller indices, that will be 2. So as we discussed in the previous topic, that negative Miller indices values are denoted by a bar on top. So these are the Miller indices that you can give for the direction, in the direction part, and you know that the 2, minus 3 and 2, and minus 3 is your negative Miller indices. So that's why minus 3 can be represented as 3 bar and 2, 2. So this is not in the first bracket, because as you know that the it's basically represented direction. Okay, Miller indices used for both plane and direction, and this Miller indices indicate for as a direction. So that's why it is basically within the third bracket, and if it is a first bracket, so it represents a particular plane. Okay, if it is a second bracket within the 2, 3, 2, so that will be a family of plane. Okay, so these are the notation part of a particular Miller indices. Okay, so you have to carefully on it. And now plane. Okay, plane. Now suppose, so these are the plane. Okay, this is the plane which intersect at a particular point. Now this is the cubic cell. As you know, that is a and A, the distance between two atoms. In a cubic unit cell, we are assumed that the distance between two atoms, we are assumed that the value is 1. Now if it is 1 here, and this plane identified with the intercept that is basically 1, and there is no particular meeting point as in y-axis and z-axis, but in parallel to the as well as y and z axis. So that will particularly infinitive that will meet with infinity point. So intersect point for a particular x, y, and z axis will be 1 comma infinity and infinity. Now reciprocal, if you second part will be to calculate the Miller indices, that the reciprocal of the particular intercept point. Then reciprocal will be 1 by 1 divided by 1 by infinitive and 1 by infinitive. You can get 1 0 0. Now that for this case actually for Miller indices will be in the first bracket 1 comma 0 comma 0 and first bracket close. So this is represent a particular plane and this represent a particular direction and Miller indices. Okay, so that's why it is within the third bracket and this is for first bracket. So this is the representative. You don't use that particular comma here, don't use, because Miller indices is represent h means for the value 1 here, k is 0, l is 0 and within the first bracket. For a particular plane, if you represent a plane in a Miller indices, that within the first bracket and the numbers. Okay, similarly for the direction, the numbers that represent a particular Miller indices and within the third bracket. So that's all. And one more thing, that negative Miller indices value is basically written as a the number on the top actually bar. Okay, so and one more thing, that so these are the representation part. As you know that these are the plane. So these are the plane actually. This plane is represent, the plane is 1 0 0 1 0 0 and as you know that 1 0 0 means 1 infinitive infinitive. So 1 0 0, this plane actually 1 0 0. Okay, so this is 1 0 0 already on this. Similarly 0 1 0, that means 0 means, so these are the plane. Okay, now you have to convert what is the intercept point for that. Infinitive 1 infinitive, x y, x direction is infinitive, y in direction is 1 and z direction infinitive. So these are the plane. Similarly for plane 0 0 1, so suppose plane 0 1 0. Okay, so plane 0 1 0 0 1 0. So these are the Miller indices which indicates a particular plane 0 1 0. Now what is the intercept point? So intercept point will be the reciprocal of that particular Miller indices number. Okay, the reciprocal on a particular Miller indices number. So that will be 1 by 0, 1 by 1 and 1 by 0. So 1 by 0 means, so these are the reciprocal part and that will be 1 by infinitive 1 infinitive. So basically in x intercept with infinitive, y intercept at 1 point and z intercept and infinitive. So basically y direction, so this is a xyz plane in which y direction in this direction. So y is your 1 here. Okay, so this point, and x is infinitive and z also infinitive. So x is infinitive means, so these are the plane x is infinitive, so that meet together as infinitive and z is all infinitive. So this will be plane this one. Similarly if you can calculate 0 0 1, that will be this one. So 0 0 1 means again for 0 0 1, so it is a plane. Okay, so this is the plane of 0 0 1. That means it's cut with the plane reciprocal of that 1 comma 0, 1 by 0, 1 by 1. So that will be infinitive infinitive 1. So x direction is infinitive, y direction is z, intercept point and z direction is 1. So x y both infinitive, z 1. So this is the x y z plane. Okay, so x y z plane, z axis actually, and plane is 0 0 1. So what is the point here? That so z is 1. Okay, fine. Now x is infinitive and y is infinitive, so this is the plane. Okay, similarly you can draw the defined plane 1 1 0, like 1 0 1, 0 1 1 and 1 1 1. So 1 1 means, because as a cubic unit cell we assume that a is equal to 1, so this is 1 this also 1, because this is basically indicate is y and x and z. So x is equal to 1, y is equal to 1, and z is equal to 1. So if you then, so if it is the plane is 1 1 1 Miller indices, the reciprocal will be 1 1 1. The intercept point will be 1 1 1, because 1 by 1 1 by 1 1 by 1 is basically your reciprocal point, and this is your intercept point. So 1 1 1. So in x axis 1, y axis 1, z axis 1. So connect this line, so it will be forming in this area. So this is your plane 1 1 1 plane. Okay. Okay, in the next class we take on another example on Miller indices. Okay. Okay, thank you very much for listening and watching me, and goodbye.